Hello and welcome to Chapter 3 of Elementary Statistics with your instructor, Dr. Gutierrez. We'll be looking at describing, exploring, and comparing data. Now, so far in the first two chapters, we've looked at different kinds of data as well as different methods of collecting data. Now we're going to look at how do we describe that data we just collected. Alright, we're going to go over three sections. First, measurement of center. What does it mean for something to be the middle of a measurement? We'll talk about a few different examples of that. Measures of variance. How do we explain how distributed this data is? And finally, section 3, we'll be looking at measuring of relative, standing, and box plots. So here we're looking at z-scores, which will be introduced for the first time. We'll also be going over those much later in other chapters. And box plots, the one and only time we go over these things. I think we'll go over them one more time. But box plots are not too used in most of the statistics I'm familiar with. In this video, we're just going to go over section 3.1, measurements of the center. Alright, so we got mean, median. We'll also talk about something called mode, although that's not really a center that we talk about. And there are a couple of other center ideas that we shall explore as well. But these are just the key words for now, and we'll get to know about them a little bit more later. Alright, so when we talk about the measure of a center, we're talking about what is at the center of the data we collected. Alright, what is at the middle of the heights of men in a certain class, for example, or the heights of women in a certain class? How could we compare those two, and is there a significance to that comparison? So first one will be the mean, or the arithmetic mean. All right, we add up all the data we have and divide by the number of data that we have. So if we have 15 men in the class, we get all of their heights. We add all the heights together and divide by the total number of men we have in the class. And that would be the arithmetic mean. All right. Bad thing about the arithmetic mean is that it is not considered resistant. That means if we have someone who's 10 billion feet tall and everyone else is 5, that one person who's 10 billion feet tall, well, they'll probably suffocate because that high, I don't think you're going to be able to breathe much. But outside of that, they're also going to mess up the statistics. The mean is going to be very high, and so that is not going to give us a good measure of the center. If you're working for a company like Microsoft, for example, and they give you the mean salary, and that includes all the money that Bill Gates gets, that's probably not going to be a good example of what you can expect if you start working for them. So that is some of the issues with mean. So those examples are called extreme values, or they're called outliers. In other words, parts of the data that are very far off from most of the data. So when we say resistant, you kind of get this idea already. A statistic is resistant if the presence of extreme values does not cause it to change very much. The mean is not resistant. Alright, notation-wise, we're going to have some notations here. We're going to have this thing that looks like a M on its side. That's actually a sigma. It's a capital sigma. It's a Greek letter. It denotes the sum of a set of data values. And usually you'll put what you're interested in getting the sum of after it. So sigma of x sub I, for example. X is the variable that we're talking about, and it represents each of the individual values. Little n represents the number of data values we have in a sample that we have collected, and big N would represent the number of data values we have in an entire population. If we did a phone poll of 1,024 people in the United States, that would be little n is equal to 1,024. Big N is equal to 300 million. 350 million maybe. Alright. X with a little line on top is called X bar, and that is equal to the mean of a sample, and that is X bar is equal to sigma X over little n. Mu which is that little Greek letter there, looking like that. And it is the mean value of all of the population. So mu is equal to the sum of all the x's over big N. Alright, now in most cases what we will be able to calculate is x bar, and from that we will try to determine what mu is. Alright, so let's talk about a little bit of this, these examples here. So let's say we want to type that equation x bar is equal to sigma x sub I over little n, or even mu is equal to sigma x sub I over big N. Well, we can either click on insert equation, insert, go to equation here, and this is a Word document, even gives us some suggestions right there. I will usually do alt equals, and that will automatically give me that. Now, to put the sigma, you can do slash sigma like this, and this will give you a sigma like that, but it's a small sigma. It's not a mathematical symbol. So usually for that, I will do large operator, and I'll get a sigma like that. So sigma, I want to get x sub I, so I do an underscore I, and that'll give me x sub I. I want to divide that whole thing, so sigma x sub I divided by n, and that's a little n, so that's going to be the sample. So I will write that as x bar equals the sum of x sub I over little n. Now, if I want to write mu, I will write little mu like that is equal to, again, go to click on equation tools, just because the sigma operator doesn't really look good unless you put it in that. From there, x sub I divided by, divided by big N. Right. And so that gives us our operator that's there. X bar is equal to this. Sigma, or mu, is equal to that. Now, let's go back to our PowerPoint. So x bar is the mean of the sample. Mu is the mean of the population. Alright, so some examples that we're going to look at. Mean airport data speeds. In Appendix B includes the measurement of data speeds of smartphones from different carriers. Find the mean of the first 5 data speeds for Verizon. You'll notice this computer likes Verizon. They give it really high numbers. AT&T, they're like 0.2, 0.7. Verizon, 38, 55. I don't really know which one is better. So this is Mbps, so that's megabits per second, not megabytes per second, but megabits per second. Don't let them fool you with that. So we want to figure out the mean. So the mean is just we add this, add this, add this, add this, and add that and divide by 1, 2, 3, 4, 5. Right? And they're going to show us that x bar is equal to the sum of all those divided by 5. Now, if we want to do that, we can also do that in Excel. So here you see I have the Verizon speeds in megabits per second. I should close off that parenthesis there. And we got 1, 2, 3, 4, 5. So I can say, what is the sum of everything here, so all of those, divided by 5. And there we go. It gives us the mean of 30.74 megabits per second, which is what we have here. Alright, they're going to give you a caution here. I'm going to tell you to disregard this caution. Okay, never use the term average when referring to a measure of center. The word average is often used for mean. The word average is pretty much always used for mean. I use the word average for mean. I have never seen it used for another measure of center, and there may be places where it is, so maybe you want to keep this in mind, but at least for me, I've seen the term average used by statisticians, I've seen the term average used by journalists and the statistics community. I've seen it used in physics. That's heavily dependent upon statistics. So if you say average, I will assume mean. And if I say average, you should assume mean. All right, median. All right, median, you can think of the median of a road. It's going to be the middle of the road. Right? You got one lane going one way, one lane going the other. You have the median in the middle. That's what we're talking about here. All right, and this is the middle value when the original data values are arranged in order of increasing and decreasing magnitude. So the median does not change by large amounts when we exclude or when we include a few extreme value points, as long as we have a lot of data, a robust amount of data. Right? So this would be considered a resistant measurement of center. All right, so median can be denoted by x tilde or big M or med. X tilde or just median is usually what I've seen from it. Now, the middle is really easy if we have an odd number of data points. We simply have to pick one of the points. If we have an even number of data points, then we average the center 2. Alright, example, find the median with an odd number of data points. So this is the same data we had before, 38.5, the Verizon data. Put it in order and find the middle one. We add a data point, 24.5, and now we're going to have 2 points in the middle. We put them in order. The 2 points would be 23.1 and 24.5. Add those two, divide by 2, and we get 23.8. Now let's take a look back at our data here. Now we can order this data if we want. We simply click on this and sort from smallest to largest. So we got 1, 2, 3, 4, 5. So this will be our median. Right there, 23.1, exact same thing they did. Now, for this next one, they added 24.5, so we can go ahead and do that. So we can add, well, let me copy this data over here. And I will add 24.5 here. Again, I order it. Really gonna do this to me? Right here in my connection? Whatever. Alright. I don't need that. Alright, anyway. 24.5. It's gonna be right there. Cut you guys down. There we go. Ha! That'll teach her. Alright, now we got these two in the middle. Doop, doop, doop. So we simply take these two, add them up. So equal, and now rather than saying the sum of those two divided by 2, I can just say average of these two. 23.8, which is our median. Now if I simply take all the data and do that, equals average this will be our mean. So a mean of 30.74, a median for the 5 data points of 23.41. For the 6 data points, we would have a mean of equals average, open parentheses, get it all. I got an extra one, that doesn't matter. 29.7. This will be our average in Excel. And this will be our median. 23.8 megabits per second. All right, mode. All right. This would tell us what occurs most frequently. Now, there was an exam. It's a math competition called the Putnam exam. You might want to look it up. It was kind of fun. Anyway, the mode for this test was 0. In other words, about 70% of the people got a 0 on it. If you got a 1, you were in the 75, 80%. I got an 11. The highest was 126. There were 12 problems, 10 points each. I got 1 problem. So, yeah, I got way above the mode in that one. Mode can sometimes be misleading. Cases like that where you have a bunch of zeros, or if you have a bunch of 100s. I have been known to make exams too easy and just have everybody get 100. Probably not this class. But maybe. Who knows? Alright. So mode is just whatever occurs with the most frequency. Alright, we're going to be looking at that with quantitative data. Data can have no modes. It can have 1 mode, or it can have multiple modes. And we'll talk about how that can happen too. Right. So 1 mode is if we just have 1 number that's the most frequent. So something can be bimodal if we have 2 things that are just as frequent. So if I have the scores 0, 0, 50, 100, 100, that would be bimodal. Twice 0, twice 100, 50 was just once. Multimodal would be if you had data where there were a lot of different modes. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10. That would have 9 modes. Unfortunately, only 5 would not be a mode. You also have data where there are no modes. In other words, there's just 1 of each point. In some books, you'll actually hear that referred to as everything being a mode. It depends on the book. Right. So Sprint, not Verizon, now Sprint. I think I said AT&T earlier, but Sprint, so much worse. Look at that. 0.2, 0.3, 0.3, 0.6, 0.6, 1.2. So the mode is 0.3 megabits per second is the data speed. All right, very bad data speeds there. All right. Now if they have this data, 0.3, 0.3, 0.6, 4, and 4, 2. Because 0.3 occurs twice, 4 occurs twice, and if they're all different, as in this example here, we have no modes. Mid-range. Okay, never have heard of mid-range before this class. It is a very bad measurement of center. You take some maximum value, you take the minimum value, you divide it by 2, you call that the mid-range. Sometimes it's used for things that are evenly distributed if you just want to find the middle of something, center of something. But trying to present it as something useful of data that is probably going to have some non-uniform distribution probably isn't going to help too much. Mid-range is just maximum value plus minimum value divided by 2. That's it. Not resistant, obviously. If you have a real big extreme in one end and a real big extreme in the other, it could lead to bad, inconsistent, and useless results. Alright, benefits of the mid-range, easy to compute. You take 2 numbers, add them up, divide by 2. Alright, mid-range tells you that there are different ways to get the center, some better, some worse, like mid-range. And it can be used if you have nothing else, just to give you a quick and dirty idea of what the median or mean may be. All right, go back to our Verizon data. We got 38, we got 55.6, da-da-da. Mid-range is maximum plus minimum divided by 2. 55.6 plus 14.1 divided by 2. And that'll give you the mid-range of 34.85. Alright, so we got some round off rules here. Carry 1 more decimal than the present value has. Alright, mode, leave without rounding. All right, critical thinking. Good points here. Our data has to be numerical, and you have to be counting or getting a measurement of something. If you have data that is just random numbers, then the median mode, none of that's going to make any difference. Example is the zip codes that we could have for a bunch of different places. 63102, 20500, 20330, 10118, 10004. Hell, 90210, we can throw that one in there if we want to. You average them, they're not going to give you anything because you're not counting anything. Now, if they were longitudes or latitudes, that might give you something, but in their present form, they're not. Right. Same thing with rankings. First, second, third. You can average those. Again, not going to give you anything. Alright, you can also calculate a mean from a frequency distribution. If you know you got 10 of these and 5 of these and 4 of these, you'll simply get the sum of the frequency times x divided by the sum of the frequencies. And that'll give you the total number of samples that you have. And this one's going to go back to the McDonald's problem. So you have your times here, you have your frequencies here for each of these ranges. And for each of the ranges, you calculate a midpoint, and then simply multiply the frequency by the midpoint, and get this sum here. Frequency times the midpoint, get this sum here. Frequency times the midpoint, here, here. And then add all these up. This will give you the sum of f times x. And this will give you the sum of the frequencies. Take this, divide it by this, and you will get your average in that way, 160.5 seconds. Now that's one way that you can get your average from the frequency distribution, but really you already had this data here. You had the exact times, so there was no reason to go through this. This is just giving you an example of that. Let's take another look at an example. Well, I'm going to go back to here, and let's say I am rolling 2 dice. Well, I could roll a 2, I could roll a 3, talking about the sum of the 2 dice, anywhere up to 12. So I'm going to say, well, let's go back one actually. It's going to be 2, 3, 4, 5, 6, or I could do 2 6s that would give me 12. This is equal to 1 plus that number above. So I now have this formula. And I simply copy it here, Control V, Control V twice more, copy, V. Alright, now, I could get a 2, I could get a 3, I could get a 4, 5, 6, 7, 8, 9, 10, 11, or 12. Now, how many times could I get each one of these? Well, I could get a 2 in one different way. I can roll a 1 and a 2. I can roll a 3 in 2 different ways. I can roll a 1 and a 2, or a 2 and a 1. That would be 2. This would be 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. 5, 4, 3, 2, and 1. Because again, we just have one way we can do 12. So what would my frequency distribution look like? Well, here would be f, and here would be x. Right. So what I can do, if I wanted to get the average of what I would roll here, is simply take this, multiply it by this, and that would give me a value here. That equals this number multiplied by this number. And that'll give me a 2. This is f times x. So simply copy that and paste it all the way down. And then if I just get the sum of that, so sigma of fx, this is simply equal to the sum of all this, and we get the sum of all this. Then our x bar is simply equal to this divided by that, which is 7. In other words, we would expect on average that we would roll a 7, which is indeed what is most probable. Alright. So that is from a frequency distribution. Now, a weighted mean, and this is what's used for grades, including grades in this class. Right? We have a weight to each score. We have a value to each score that you get in there. Divide by the total number of weights, which ideally should be 1 if you do your percentages correctly, and that'll give you your average for the class. This is also how GPAs are calculated. So, let's take a look at this person. In her first term, in her first semester of college, a student of the author took 5 courses. All right, her final grade, I don't know how the author got her grades for all 5 of them, but okay, guess it worked. Her final grades, along with the number of credits for each course, were she got an A, which was 3 credits, an F, or an A, which is 4 credits, and a B, which is 3 credits, a C, which is 3 credits, and an F, which is 1 credit. So, did she fail orientation? She failed a 1 credit class. I did get a C in an orientation class. So, yeah. Alright, so A is equal to 4, B is equal to 3, C is equal to 2, D is equal to 1, and F is equal to 0. So the weights are 3, 4, 3, 3, and 1. And the grades are 4, 4, 3, 2, and 0. Put them into a summation. Her GPA was, again, orientation, sad. 43 divided by 14, that gives us 3.1 for the final GPA, because you always round up. I always try to round up in my class. Alright, so down to 2 semesters. And next, we shall talk about section 2. Talk about variance. You can hear from me then.